Gravitational force acts between any two objects in the universe. One easy way to demonstrate the effect of gravitational force is to suspend a horizontal scale with two masses at the end, as shown. Now, quickly place two large masses next to the mass of the scale. If you wait and observe, you can see the two small masses will move closer to the big masses, and eventually they will stick together. This force of attraction happens due to the gravitational force. It looks interesting, right? Let's learn a few more details about the universal law of gravitation and how Sir Isaac Newton discovered this very important law. As we all know the story, an apple fell down from a tree, which started Newton thinking. Let's assume there is one more apple tree that is far away from the current tree, and an apple falls from it as well, as shown. If you analyze this way, it is clear that objects fall to the Earth in a radial direction, or the Earth attracts the objects radially towards the center. This observation was the turning point in the discovery of the universal law of gravitation. Newton realized that the Earth does not attract the objects just down, but it attracts the objects radially towards its center. It's logical to conclude that, in a similar way, the Earth is pulling the Moon radially towards its center with an attractive force. Similarly, the Sun as well is attracting the Earth towards its center with a certain force. Now let's move away from these rounded objects. With the same logic, this car will attract this book towards its center of mass. Similarly, this book will attract this car towards its center of mass with a certain force. According to Newton's third law of motion, these two force values should be equal. In short, all the objects in the universe attract each other with a certain force. This is the universal law of gravitation. Now, the next challenge. Newton wanted to derive an equation to predict the magnitude of the force which arises due to the universal law of gravitation. Newton's intuition told him that the effect of gravitational force would dilute with distance. But to what extent? To get an answer for this question, he looked at the Moon. The Moon is also attracted to the Earth due to the same gravitational force. However, the Moon doesn't fall to the Earth because the centripetal force required for the Moon's circular motion is supplied by the gravitational force. People at that time already knew the Moon's angular speed and the distance between the Earth to Moon. Based on this force balance idea, Newton calculated the centripetal acceleration of the Moon. The force acting on the apple near to the Earth's surface can be easily calculated by measuring the apple's acceleration. The value of this acceleration is 9.81 meter per second squared. Newton compared these two acceleration values with the distances from the center of Earth. Can you spot any connection between these four numbers? If so, congratulations! Anyway, Newton was able to find out a definite connection between these four numbers. Divide the acceleration values. Now, take the square of the distances and divide. Surprise! The resultant values are very close. This means the gravitational force is inversely proportional to the square of the distance between the center of the objects. What a brilliant deduction! The next question is, do the objects' respective masses have any connection with gravitational force between them? Newton had already derived the equation for an object's acceleration during this period, and it is a common observation that when the force arises due to gravity, the value of acceleration does not change based on an object's mass. Therefore, the value of force due to the universal law of gravitation should be a factor of the mass, so that when you find out the acceleration by dividing the mass factor will get cancelled. Likewise, we have to include the mass of the second object as well in this equation, in this case, the Earth's mass. This is the expression Newton derived to find out the force due to the universal law of gravitation. He introduced a constant called the gravitational constant and made it a proper equation. According to the universal law of gravitation, all the objects in this universe attract each other. In this case, the Earth attracts the apple with a force value defined by this equation. The apple also attracts the Earth with the same force value. However, the Earth doesn't move to the apple because when you divide this force by the mass of the Earth, the acceleration value becomes negligible. The case is the same with every other object in the universe. It's somewhat impossible to believe, right? Are all the objects in the universe really attracting each other? We find this idea difficult to believe because we live in a world where frictional force is always present. Just imagine a long, frictionless room with no object in it. Now, introduce 2 blocks on the floor. If the frictional force between the object and floor is 0, you would see the blocks move toward each other due to the gravitational force and finally collide. Of course, this was a hypothetical experiment. A more realistic experiment to visualize the effect of gravitational force would be placing 2 heavy balls near a hanging 2-ball arrangement. If no objects are near them, you'd observe that slowly the small balls would move to touch the larger ones. Even though Sir Isaac Newton derived the equation for the universal law of gravitation, he didn't find out the value of g. Many years later, an English scientist named Henry Cavendish came up with a clever idea to determine the value of g. His experiment was very similar to the example we saw earlier. The only difference is that his setup was able to attain a balance force between the force due to gravity and the string's torsional force. You can see clearly that when the torque produced by the torsion of the spring is the same as the torque due to the gravitational attraction force, the balls balance. Using this twisted angle at the balance as an input, Cavendish calculated the value of g for the first time, that too quite accurately. We hope you now have a clear understanding about the universal law of gravitation. See you next time.